Hi friends, this is the 11th lecture in the lecture series for the preparation of gate in mechanical engineering, and today we are going to discuss the fins only, but we are going to discuss the heat transfer rate through various tip conditions, and then we will be discussing about the effectiveness of fins, and then we will be discussing about the efficiency of fins, and this effectiveness is denoted by epsilon, efficiency by eta. So this is the continuation of the last lecture, so please go through the last lecture to get a better understanding. So let's start by writing the general fin equation. So the general fin equation will be d square t by dx square plus 1 by ac dac by dx minus h by kac into das by dx into t minus t infinity is equal to 0. So this is the general equation of fins. So if we are provided with a fin of constant cross sectional area, and then the terms that are present in the last equation, that is dac by dx will become 0, and this das by dx will be equal to p, which is nothing but the perimeter. So applying these conditions into the previous equation, and write down the equation as d square t by dx square plus 1 by this 1 by ac term will be 0 minus hp by kac into t minus t infinity will be equal to 0. And let's suppose this t minus t infinity is equal to theta, and dt will become d theta, and let's suppose hp by kac is nothing but some value square, that is m square. And applying these conditions into the previous equation, we can write d square theta by dx square minus m square theta will be equal to 0, and this is the general fin equation for constant area cross section fins. Then the solution of this particular equation will be theta is equal to a e raised to mx plus b e raised to minus mx, which is nothing but the solution or the general solution. If you want to find the solution for various cases or the solution value, then we have to determine the constants a and b, and to find the constants a and b, we have to define two boundary conditions. And the first of the boundary conditions are given from the tip conditions. Okay, so in this, the first boundary condition will be given from the temperature at the base. That is at, suppose let some fin is there like this, and this is the surface over which the fin is attached, and this is the fin, and which is having some length L, and this is the x-axis and this is the y-axis, and this is the point in which x equal to 0, and this is the point at x equal to L, and this area is called the base. So at x equal to 0, we have temperature T is equal to Tb, and at x equal to 0, the temperature difference, that is theta, is equal to T minus T infinity will be equal to theta b, that is Tb minus T infinity. So these are the boundary conditions at first boundary condition, and the second boundary condition will be available from various tip conditions. And depending upon what is the type of tip that our fin is having, then the second boundary condition will vary, and these types are nothing but some fins in with in which we are having infinitely long fins, and for this particular case we have t at x equal to L is equal to t infinity, which implies theta will be equal to 0. Okay, since this is t infinity minus t infinity at x equal to L, which is nothing but 0, and this is the first kind of boundary conditions. And second one will be, or the second tip condition is nothing but insulated tip condition, and in this case we are having no temperature difference at x is equal to L. So therefore dt by dx at x equal to L is equal to 0, which implies d theta by dx at x equal to L is 0. So this is the second boundary condition. And the third boundary condition, which is nothing but the convective tip condition, and for this convective tip condition we are having minus k dt by dx will be equal to h into delta t, and this is nothing but minus k d theta by dx is equal to h into theta. So this is the third boundary conditions. Okay, so depending upon the temperature at the base and various tip conditions, we will be having various solutions for this particular equation theta is equal to a raised to mx. So let's suppose first type of fins, in which we are having the infinitely long fin, and for this particular type of fin we are having the fin like this. This is at x equal to L, and this is at x is equal to infinity, and we are having some length of the fin L is equal to infinity. And for this particular case, here we are having t is equal to tb, and here we are having t is equal to t infinity, and theta is equal to 0. Here theta is equal to theta b. So these are the two boundary conditions existing on these sections. So applying these boundary conditions into the general solution, we can determine the solution as theta by theta b, and the solution for this particular case of infinitely long fin will be equal to t minus t infinity by tb minus t infinity is equal to e raised to minus mx. Okay, so next we have to determine the heat transfer through these fins, and this is given by the equation q dot is equal to minus k ac into dt by dx at x equal to 0, and applying this equation we can write minus kac d theta by dx at x equal to 0, and differentiating the above equation we can write minus kac d theta by dx, that is theta b into d theta will become e raised to minus m into e raised to minus mx. Okay, and this minus and minus will cancel, then we can write kac theta b into m into e raised to minus m into 0. This is at x equal to 0, and then so we can write this q dot is equal to kac theta b into m, and we know that m is nothing but kac into root of sp by kac, that we already mentioned in the general fin equation for the constant area cross section direction. So kac into root of sp by kac into theta b, and we can rewrite this equation as root of sp kac into theta b is nothing but the heat transfer rate. Okay, and this root of sp kac, these are all constants, so we can illustrate this as m into theta b, where m is nothing but root of sp kac, and please note that this is capital term and this is nothing but sp by kac, and this is small letter m. So heat transfer rate is given by the particular equation. So that's it, that is the heat transfer rate for this infinitely long fin. And then we will be dealing with the second type of tip condition, that is insulated tip condition. For this insulated tip condition, we are having fin like this, where some insulation is provided at the tip like this, and for the since the presence of insulation will not allow any kind of heat transfer insulation. Over here the temperature variation T will be equal to the TB, and we are having the dt by dx at this x is equal to L will be equal to here, that is x equal to L, and here x equal to 0, and at x is equal to L, dt by dx will be equal to 0, that is d theta by dx will be equal to 0. Here we are having t is equal to tb and theta is equal to theta b. So these are the boundary conditions that we are going to apply in this particular case. So we can write the equation or the solution as theta by theta b minus is equal to t minus t infinity by tb minus t infinity is equal to cos h m into L minus x by cos h m L. Okay, so to define the heat transfer rate, we know that q dot is equal to minus k AC into dt by dx at x equal to 0. So we can rewrite this equation as minus k AC into theta b into or we can, before that we can write this is d theta by dx at x equal to 0, and this after differentiation we can write minus kc into cos will be changed into sin hm into L minus x by cos h ml. Applying this at x is equal to 0, we can write this as KAC into sin by cos is nothing but tan HML, and there is a theta b term over here into theta b, tan HML into theta b into m. Okay, so we can rewrite this equation as root of HP KAC into theta b into tan h ml. So we can write the heat transfer rate is nothing but m into theta b into tan h ml, and where this m is nothing but the root of HP by HPKAC. So that is the heat transfer rate through fins in which we are having the insulated tip. And the last type of fins that we are going to analyze is convective tip. And for this particular kind of tip conditions, that is we are having some fin like this and some heat transfer rate or some fluid is flowing like this, and we are having here we are having some heat transfer like, and we are having H or convective heat transfer over there, and this is the x equal to L. And for this particular fin we can use the same equation as that of the heat transfer rate equation that we used in the insulated tip, that is m into theta b into tan h m L c, where there is only a slight difference in which the LC is nothing but the characteristic length, and this LC is given by L plus cross sectional area divided by the perimeter. And if we are having some rectangular cross section fin, a rectangular cross section fin, and this LC will become L plus B, T T by 2. And if we are having circular cross section fin, we are having characteristic length LC will be equal to L plus D by 4. Just apply these two values of characteristic length LC into the equation for the insulator tip boundary condition where LC is there. Then we can calculate the convective tip heat transfer rate. So that's all about the heat transfer rate for various tip conditions. Since we are having tips or the fins that are connected to some kind of body, we have to find what is the effect of this fin. For that case, we are defining the term called the effectiveness, which is denoted by the letter epsilon. And this epsilon is nothing but the q dot with fin divided by q dot without fin. That is nothing but the ratio of heat transfer with fin and the without fin cases. Suppose we are having some surface like this, and there is some fin is attached over here, and this fin is having a shape like a rectangle over here. Okay, so this is the surface over which the fin is attached, and so this is the fin that we are having. Let's suppose this is the cross section over which our fin is attached. Okay, so this here we are having a cross sectional area AC over here, and the heat transfer rate with fin will depend upon the type of tip condition that we are using for this particular tip, but the heat transfer rate without fin will be constant, and this will be given as H into AC into theta B, where theta B is the temperature difference at this base of the fin. So this is the heat transfer rate without fin for every cases, and this effectiveness can be calculated for various tip conditions, like effectiveness for infinitely long fin. We can write the q dot with fin as m, or rather HPKAC into theta B divided by q without fin is H into AC into theta B. Cancelling all the similar terms on after some manipulation, we can write this effectiveness infinitely long fin will be equal to root of HPKAC. Okay, so this is the equation for this particular infinitely long fin case. And for insulated tip condition fin, we are having epsilon is equal to q dot with fin by q dot without fin, and this will be equal to m theta b tan HML divided by HAC theta b, and this will be equal to root of HPKAC into theta b by HAC theta b into tan HML, and this will be equal to root of HP, which can be written as HPKAC into tan HML. So this is for the insulator tip. Okay, so this is the effectiveness of insulator tip condition. So that's all about the effectiveness. So we are having some fins in which the effectiveness we have calculated, but in all these equations of the effectiveness we can see some common inferences, that is epsilon is proportional to K, and this is nothing but the thermal conductivity. So use high thermal conductivity material and we will be getting high effectiveness, and that is nothing but the heat transfer rate will be more. Okay, that is the first case, and also we can infer that it is proportional to K by AC. Sorry, it's proportional to P by AC. that is perimeter by area of cross section. And in this we are having which means that thin fins are more effective. Thin fins are more effective. So that's given by this particular ratio, and we can also see that this is proportional to or inversely proportional to 1 by h, that is the convective heat transfer coefficient. That is that will be a common understanding that for low convective heat transfer coefficient flows for the heat transfer we are using the fins. So the next we can see that if we are designing some fins in which the effectiveness is less than 1, then it is not advisable, or it is not the case that effectiveness will always greater than 1. If some poor design will cause the effectiveness to become less than 1. Okay, so if we want to use the fin effectively, so this epsilon, that is effectiveness, should be greater than 2 to get better results. Okay, so that's all about the effectiveness. And next we will be dealing with the efficiency of the fins, and which is denoted by the letter eta, and this efficiency is given by q dot actual by q dot ideal, or the maximum, ideal or maximum. And this q dot ideal is nothing but the heat transfer rate that we are getting, heat transfer rate that we get when the fin is having uniform temperature or arc conduction to be minimum. Okay, suppose if we are having some fin, what happens is that arc convection will be reduced in a drastically, but the arc conduction will increase because of the presence of this extra material that is given by the fins. So if we want to reduce this arc conduction to be 0, or particularly which is the ideal case, what we have to do is we have to keep the temperature at every part of the fin as equal to base temperature Tb. Okay, so this is some ideal case. So the heat transfer that we are getting at this particular case will be, for this ideal case in which the temperature of the entire fin surface equal to Tb, we are having the heat transfer rate q dot is equal to HAC into theta b, where this AC is given by H into PL into theta b. This is the ideal heat transfer rate. So applying this equation for various tip conditions, we can find the efficiency for various tip conditions as efficiency of infinitely long tip, and we can find the q dot actually is nothing but root of HPKAC into theta b by H into PL into theta b, and cancelling the terms and doing some manipulations. After some manipulations, we can write down the equation as, that is HPKAC root of into theta b divided by H into PL into theta b. After doing some manipulations, we can write this as 1 by ml. Okay, and for efficiency of insulated tip boundary conditions, we can write this as HPKAC into theta b into tan h ml divided by H into PL into theta b. So we can write this as cancelling theta b and theta beta, which can be written as tan h ml by L into root of HP by KAC. So this is nothing but tan H ml by ml. Okay, so this is the efficiency of insulated tip film. So this is the efficiency, and these are the